it's on, so that's good. All right, so, oh, he just responded. Oh shit, where can I join? It is in the FAF Discord. Hashtag game development. Oh, he's here. All right. Don't worry about it. It's fine. All right. So just so everyone's clear, this is being recorded. The idea is that it gets on the FAF YouTube channel at some point. Yeah. Now you know. And well, it's better to have it there than to have it on my own personal YouTube. And if you're uncomfortable with that, with having your voice in there, if in case you have questions, then please just send me a text instead, and then we'll do it like that. So the idea of today's session, I'm just gonna show how I would approach two functions in terms of how to optimize that. Let me share my screen. There we go. Say again. Yes, yes, we're going to look at some of the UEF things, yes. Let's see, and for a change, I'm not going to branch from FAF to FALAB, but from the branch of Takada he did last week, because he did some changes that we need to take into account. Whoops, there we go, get checkout. Checkout, be optimize UEF effects. Alright, so there's two functions in particular. We'd like to look at the create default build beams, which is used by a lot of engineers if they don't know how to deal with a structure. For example, UEF engineers use that if they are assisting a structure of another faction, or if they are assisting a unit, or if they are assisting, for example, a strategic missile defense. So it's pretty commonly used. And we'll be looking at another function which was create UEF build slice beams. And we're not going to be able to finish this one because this one is pretty big and it has a lot of components to it. So we're going to finish up the create default build beams function, and then we're just going to skim this function and see what are they doing and why is it so inefficient what they're doing. Just to show you that there's more that we can do than just rewrite the code. We could also, for example, apply mathematics, and that is what we can see in this function right here. But let's start first with the other one, which was create default build beams. There we go. All right. I assume you have the development environment set up. That means that any change we make to the repository will be live. Now there's a couple of gotchas that we're going to have to handle and to deal with. First of all, in terms of efficient development, if I now save this file, then we know that our changes are being recorded right now, and that's because we enabled this squatch. That's one of the program arguments. That's part of the bat file right here. That is what enable this squat does. So anything we change on disk, we get immediately in the game. But there's a catch, because for example, if we make an engineer and we add a strategic missile defense as an example, and we would be assisting the strategic missile defense, and now we make a change just by adding a log statement to make sure that we're having the right function here, then the log statement doesn't show. And that's because the change is recorded, but the class, the instance of this class, is not being updated. which means that if we would make a new engineer now, this little fella, and we would tell it to update, then now suddenly we do see our log statement here. Right, so anytime you make a change, it's important to realize that any class that already existed before you made the change does not inherit that change necessarily. There is a hack that you can enable that, but I'm not going into that hack for this session because then it gets a bit much. That will be for another session. But let's just start by looking at what we've been given. So the idea is that we're gonna optimize this function here. The pattern I've been using in the past is because when optimizing, you add in comments, you add sometimes a bit of convoluted code because you want to skip a for loop, etc. So functions tend to get a bit bigger. So to prevent this file from exploding, as it already is in some fashion, what I did at the end is just import from other effect utility files, specific in this case to a faction, to keep everything pretty clean in terms of if you're looking something related to Seraphim effects, then you need to be in effect utility Seraphim. And you know that all of these functions do not interact with all of the other functions in effect utilities, etc. So in this case, we're going to do the same thing. Let's just effect utilities UEF, and there we go. And we go to create default build beams. We just get that one out, and at the very bottom we add a reference importing this function again. This is just to keep the code a bit more maintainable in terms of not having to go over very extensive files that happen quite often, as for example the unit class is about 4,500 lines long. Yeah, exactly. And this keeps it a bit more clean. Alright, so this is the function that we're dealing with. Let's make sure that our changes actually worked out. No errors, that's nice. Let's kill these two because they use the old class. Nope. Alright, yeah, of course. So we're missing some imports here. That's what the error is saying. We don't know what entity is. So let's go at the very top and just grab all of these imports here. There we go. Take you out again. All right, there we go. All right, so anything we change in here now is going to be impacted by the game. Let's just first look at the code and just look at what we have. First of all, there's the effect itself is quite similar. We have, if we look at the bones, there we go. You can do that by Alt-V and then Alt-B for the bone names. If you're wondering what other hotkeys there exist, there's a debug tab here. And inside that debug tab, there's a whole range of things you can toggle. And in this case, we use the wireframe skeletons, which is the wireframe itself, and we have a toggle bone display for all units. So in this case, for this unit, we have a beam from this bone right here to some arbitrary point that resides in this inside the defense itself. The bone that we're originating from is this argument. So let's just print that out, see what we have. The builder is by all means the engineer, and the unit being built is in this case the strategic missile defense. Let's quickly look at what we have in terms of that value. Alright, so here we can see we have a table of turret muzzle, and this is turret muzzle. If we have an engineer with multiple muzzles, like this one has 3 of them, or 2 of them, then we can see that it's now a table of 2. So this is a table. This is a trash bag. So trash bag is defined. That's just another class. The trash bag is designed in such a way that it's easy to keep track of entities that you need to dispose of the moment that your unit dies or the moment that an effect stops, etc. And it has two functions, the add function to add something to it and the destroy function to take out everything. The destroy function is idempotent, which means that if you call it twice, then it tries to do the same thing, but it doesn't cause a crash. All right, so that's the input. These are units, that's a table. Units. All right, that's not supported. That's weird. I can't make comments in here. Okay, well, yeah, maybe. Let's just quickly check that. Does this crash? Where's my new unit? Okay, so the game's a bit laggy because I'm streaming and yeah, it appears to be just VS Code. So this is just units, and then we have table of bone names, and then we have an effects bag, trash bag. All right, I always do this, and the reason is quite simple. Lua is not statically typed, so you have no idea what you're dealing with, and it's really important to make sure that you understand your function arguments here. So let's look at the actual function. We're creating an entity, allocation of entity. We warp that to some location. That location is the unit that we're building. Then we have a table creation here. We've got some beam effects, attach and beam entity to entity. Those are stored in this table. They're put into the trash bag too. Then we've got the emitter. These are the sparks that we're seeing. So that's the sparks of these little effects that we have. And we've got some arbitrary wait time, and then until either the builder or the unit is destroyed, this keeps happening, or when the thread that is running this function is killed. So that's roughly what's going on. Now let's look at some optimized perspective. We're allocating a value here into a local, which means that this increases our stack. That's a bit of a waste because we're not actually doing anything with it, meaning we could just do this. There we go. First optimization. Then if we're looking at what we're doing here, so unit get position, what that does, this returns a table. So this is a table of some XYZ elements. And then what unpack does is it takes a table and it essentially returns 3 arguments. Now in this case, there is an alternative for this. And that's part of entity. We have get position, and we've get position XYZ, and that prevents the table allocation, which is what we want, because tables typically reside on the heap, and any allocation we can prevent from the heap is a win. So we can change this entire thing, XYZ. There we go. We're creating the entity. There's not much we can do about that because we want to have an arbitrary location in the strategic missile defense. There are some effects, for example, the reclaim effects, that always use the center of the entity. In that case, you don't have to create a separate entity. You can just use the object that you're reclaiming. But in this case, you want to be somewhere inside the object. So we're going to need this one. But this is an interesting function right here, what's happening. So what does factor do? Let's just return Let's just see what this does real quick. All right, so here we go. This returns apparently a table of some sort with a meta table attached to it and some numbers in it. So let's look at that meta table. Yes, go for it. Good question. So that one's defined in Lua as well. What a wrapper does. Yeah, I'm not really sure what the. Yeah, so let's just look at what it does real quick. That's a good question. So let's say that we have this, and let's just look at the differences. All right, so this is the output. So by default, Lua doesn't have something like toString has in C# or the show type class in Haskell. So what the GPG devs did instead is they defined this function called wrapper that essentially unpacks whatever you're giving it, and it turns that into something that looks like a string. The advantage is that it impacts everything. The disadvantage is that it impacts everything, which means that if you have a very nested table, like a unit can be, then it's going to impact all the values of the unit, even though you're just interested in one of the entries. And that can quickly mess up your logs in terms of that you suddenly have 1,000 extra lines here. So that's a bit nasty. Yes. But what do we have, right? What did vector do for us? Let's look at that. Because it returned a table that has 3 values that are part of the array section of the table, because there are no keys here, which means that this is just the first, second, and third entry. And it returned a meta table that has essentially nothing set, just an underscore index function, which is called when we do this. So if we have a value this, and we do an index operation, which is what we're doing here, then this function is called on top of that index operation. So the value that we have here is passed to the index operation, and then depending on what the index operation decides is what we're actually going to get back. So it's kind of like a helper function. And then we've got a new index function right here, which means that if we would make a new entry that doesn't exist yet, right? So v0 is nil, then this function is called to check if it's actually allowed or to do something special with it, etc. But there's nothing in here that actually is relevant to us. There's no addition operations, there's no subtraction. We still can't do this, for example. Say we have 2 of them. Then this is still not valid, right? So all we've been given here is a wrapper with a table with 3 elements and a meta table that does essentially nothing. And it gets more interesting. Say, for example, that we create 2 vectors here. Let me make this actually functional code. Yeah. See, we have this. All right. Then what's interesting here is that if we look at the memory pointers, then even though we've given it the same arguments, it returns a different table. which means that we're not only creating a new table here, or end with an empty meta table, but we're creating unique tables each time we call this function, even though the value may be the same. Which makes sense, right? Because if you're making a vector, then you want to make sure that it doesn't impact other vectors that you've made. But it also means that every time we do this operation, we are secretly allocating a new table, and that's put onto the heap, and that means that we're creating garbage. As an example, we have this function right here that does essentially nothing except grabbing these three arguments, putting it in the table, using the table once, and then the table is ready for the garbage collector to be picked up. And we have another example right here where in order to move the object, right, because that's what's happening every so many seconds, we're creating a new table just to use it once and then throw it away. So we can do better. Say we just create one of them, and I don't think you even need to use this keyword, but for the sake of it, let's do that. Then instead of creating a new table here, we store the reference of the table that we have here in our local scope. Then we populate it Yes. Yeah, that can cause some confusion sometimes, especially if you're implementing an algorithm and that algorithm expects your programming language to be zero indexed, like a heap. That's nice. But what we're doing... Oh, no, sorry. Say again? All right. Yeah. So what we're doing here is instead of allocating a new vector each time, we're reusing the same vector. And we're just using it once, and then between quotation marks, it can be thrown away or reused in this sense. For example, we could do the same thing here, where we again take this reference, but then plus x plus y and plus 7. Now there's a couple of important aspects here. First of all, every time we create a new table, it allocates new memory, but it also means that that memory, if I'm not mistaken, is also allocated in DRAM, and that makes it all a bit slow. Whereas in this case, every time this function is run, and assume that we have 100 engineers assisting this thing, they will all look at the same memory address, which means that this vector, this table that we have here, is going to be guaranteed in the L1 cache, which means that from a processor perspective, the access to this table is really fast. And that's why it's so useful to reuse that table under the assumption that after waiting, we can have no guarantees that it still has the same values. Right? Because after waiting, another engineer could have run this code and changed the values in VC. But this is another small trick that I applied, for example, to the Cybern build drones that made a pretty big difference in that case, because the Cybern build drones doesn't have one beam, but they can have multiple beams. And then if you have hives that have 6 drones, you could easily be talking about hundreds of table allocations a second just for the look of having those drones assist some factory or something else, etc. Yes, of course. Yeah.
That makes the engineers at the same point. They are running, not reusing the same vector.
No. Yes, good question. So what happens here is that we populate the vector and then we immediately use it. In the code in Supreme Commander is deterministic in the terms that there's only one piece of code being run at the same time. So there's no actual multi-threading happening in Lua. So that means that you can be assured that VC remains the same until you get to a wait statement, and then you have no guarantees about the content anymore. So what happens here is that with these engineers, if we would have multiple, let's just have that quick example, assuming it didn't fuck up, you can see that they all have unique points, right? And the reason for that is that they run this code, use it, it gets warped, and then the value is not used afterwards anymore. It's populated and then used and then thrown away between quotation marks, but we're not throwing it away because it's part of an up value right here. And in theory, yes, in theory it could be that if you You mean if you all start at the same time? Yeah. Let me try and time this. That's a bit more. So again, it's deterministic, right? So every one of these points is being handled individually, and with that, there's no issues because we populate it, use it, and then we essentially forget about it, right? And then the next engineer that's going to be run does exactly the same thing. It puts its own values in there, uses it, and forgets about it. But in practice, if you would want to store the results, so say for example that we need VC after waiting, then by all means, depending on the last engineer that did this, is gonna have his values in there instead of the ones that you were having here for your engineer, right? So, but because everything is single-threaded, you don't have to worry about that in this case. But you do get the nice benefit that this value is going to be pretty high up in the CPU cache, so that's pretty nice. Yes. No. Yeah. Yeah. Good question. So what happens if we scope out slightly is that this function is always used in the context of it being forked. So that means that we have a coroutine running, which is kind of like the fork and then wait pattern. I'm not really sure what the exact name for that is, but the idea that you create a fork and then you could potentially wait on that fork. And that means that every engineer does this. They all create their own coroutines. So essentially, if we would have, just gonna make sure, essentially we have one execution path, and then all of these engineers create their own coroutine, but they're not all run at the same time. So say for example, engineer 1 is processed first, so it starts this function with these given arguments. So let's look at the function. It starts doing what we defined in here. It starts running this and it finds this wait seconds statement. This wait seconds is defined in Lua, which is defined right here, which is essentially a yield. So we're waiting here. We're saying something else can take over. So if we're looking at it, this is where it starts waiting, and then something else can take over, and then the other thread starts here. And then that one is at some point has a wait ticks or a wait seconds or a yield, and then that one stops. And then yeah, yeah. No, there's I suspect in C that there is a queue somehow, but in from our perspective, we have 10 ticks per second, which means that we can yield up to the next tick, right?
Well, I mean more like usually we yield 5 ticks.
Yeah.
But there's like 10 ticks worth of engineers need to use this function, and then we come in again.
Oh,
Is
like
that
that.
still okay? Is that
Yeah.
right?
Yes. So what happens is that every engineer gets their own fork thread with their own execution stack, but you can have multiple threads being executed in the same tick. So technically, you could still have that this is tick, say n, and then after all these engineers are done and they're started waiting, then somewhere here, oops, let me change color. In the second tick, which would be n plus 1, some of these functions can be called again, and then waiting again. And then some of these are not.
Oh, I see.
Does that make sense?
All the engineers will have, so a tick. There's no way to stagger wait times that are in front of the
No,
ticks in that way. Okay.
no. It's just saying I want to do whatever is behind the yield in this case in 5 ticks time, and then it gets queued up in that tick.
Okay.
So that's what the waiting does, and that's an advantage that we have, also a disadvantage. The advantage is that everything is single threaded, which means that given the state of the program at this line right here, that's always going to be the same. There's not going to be another thread that's going to run through it that changes what happens between these two statements, right? So that's the advantage. The disadvantage is that we're single threaded. So
Am I right in saying that like in the function ends, we all start yielding the next, like regardless of whether or not there's wait cycles.
say again, if a function ends,
Let's say we have a function that is now just tick 0 and nothing more.
yeah.
Like Heap runs and then ends. Does that all just automatically reyield?
No. So what happens in this case is that if this is in the fork thread situation, then the thread is just deallocated because its execution path is finished. There's nothing more to do here.
But like if multiple units are using the same function or like calling the same function.
But they can use the same function as long as they're on their own thread, right? So all of these, if we look at the all of these units, let me find the engineer actually. Yeah, there we go. All of these units will use the same function, but they'll be doing it in their own on their own threads. Yeah. So all the data that's inside this function, oops. All the data that we have inside this function is unique to that thread, including the parameters, and all the data part of the closure of the function is shared between the threads. So that's why this value here is shared. That's why if you would do this,
Well, this makes total sense. My next question though is, are we or like the reference to this shared vector fashion?
yeah. So what we have is a couple of, let me find that real quick. I had a paper. There we go. We have various instructions available in Lua. And this is the instruction set that Lua 5.0 uses. And I want to point out these right here. Just real quickly. So depending on where we get a value from determines how quickly we can access that value. For example, if a value, like for example vector, resides in the global table, then what we're actually doing is this, where we actually have a table operation going on here, and that's what get global does. So this, if we would translate this one line to the intermediate Lua language that we have here, it would be a get global to get the vector, and then a function call, which is what we're doing right here. Right? This is nah. What we're doing here is a get up value, right? Because this one is part of the closure of the function, so it's an up value in that sense, which is unique to Lua, according to this paper that I was reading this afternoon. And what we're doing here is storing it in a local, so that if we use the cache here, we're not doing a get up value, we're not doing a get global, we're doing a load k. And this is very fast, the fastest form of access that you want. And because we're using this many times over, right here, 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 and continuously in this while loop, it's beneficial to have it as a local. There is obviously an overhead of doing this, of localizing a value. So you should only do it for values that are, for example, used more than 10 times or used in some sort of loop, etc. So that's why we're doing that. All right. Let's look at this. Okay, so a few other patterns that happen really often in the base code is this one right here. We have a get random float from util. Util is from utilities, so let's go there. Let's get rid of some of these. Pew. There we go. So in here we have get random float. And what this one does essentially is just calls random, multiplies it with something, and adds something to it. These are functions written for game developers, junior game developers, in terms that they prefer having a function that explicitly states what it does. Another example that Takeda fixed last week is the isThat function, which is this one here. And all this does is return the value self.dat. But what is the use of this function? Well, if you write this, then that reads easier. But from a performance perspective, this is significantly more expensive of having a getter function like this instead of just doing this. Because of the fact that in Lua, every time you do a function call, there is an instruction, this one right here, that is, there's no inlining now. Which means that if we have a function like this one that simply returns some entry of us, then we may just as well write unit.dat instead of unit colon isThat, etc. So in this case that we have right here with this get random float, we see a similar pattern. Oops. That it's just doing this. So let's just copy that in and use the right arguments, where this is 1.5, 0.3, 0.3, so we're actually multiplying this by 1.2. There we go. In practice, it's of course a very tiny change in terms of if you look at the benchmark, because I benchmarked this one. Function scope, inlining, there we go. So for example, this is an actual sequence call that was being used by default explosions. So get volume, unit volume would call get unit sizes, and get unit sizes would then return something that we just multiply here. And if we do the call sequence, it's 28 milliseconds to do this 1 million times. But if we inline it, aka we just remove the call statements, it's 22 milliseconds, which is 20 to 30% faster. But of course, it's not like the entire function is waiting for this one statement here. It's just that it's better to write it like this if we're concerned about performance, and that the fact that this is still very readable makes it nice. Then there's another interesting, because we've got this random function here, but what it actually says is this, which means that we have a get global going on here. and we can change that into an up value. Just like that. So now the access to this random function is slightly faster. And then we've got more going on here. Let's just take a step back before we continue writing, and that's this table right here. I found this one particularly interesting because what are we doing with it? We allocate a table in a local scope, which means that it's not available outside this function. We're not using it anywhere except here, where we add something to the table, and then we don't do anything with it. So we may just as well do something like this, because we're not doing anything with it. It's by all means, it's a tiny change, but any table allocation that we can prevent is a good one. Same thing here. This is a function which is part of the global table, so we can just say, and then add a comment, value for performance.
How can we check if the function is global?
In practice, if it's not defined in your current file, so if it's not part of some import and it's not another function in your file, then it originates from somewhere else, and that's very likely the global table.
So even if I attach one, it's always equal to a value.
If you have a function like this one that is generally called very, very, very often, yes, then it's very much worth upvaluing. Even though that the benefit of upvaluing, let's get that origin, I think. No, I really need to get better names in here. Right, so here we go. Get position, local, up value. So the difference is about 10%. If you have the up value version versus a global one, but I'm trying to find the one that actually tests with globals instead of the self. Oh, here it is. So if we, for example, have a very basic function like apps, then if we just access it from the global, it's 440 milliseconds. And if we just access it from an up value, then it's 277 milliseconds, which is quite a big difference. But by all means, this is run more than 1 million times. And apps is a very simple function, but it adds up. Right? If all these little droplets add up, then at some point you have a simulation that is 10% faster. And that's what we're here for. Say again? Yeah. But the advantage there is that we pay the price the moment that we read in this file, but not the moment that we do the function call. So when we import this file, which is only done once, right? So because every second time you import it, then a reference is returned. The closure is created when the Lua compiler reads the function keyword. So it reads this keyword, and at that point it makes the closure and assigns it to this function, which means that the closure, where the up value is part of, is only done once, but the function call in this case can be done hundreds, if not thousands of times in the game. So you're right, don't do this for every function, because then it may not be worth it, but for a function like this one, it's definitely worth it. Another one. And then we're slowly starting to get there. So there's get random offset. Let's look at that, which is part of unit.lua. This is one that used to be pretty terrible, but Jakarta already fixed this in a pull request. There was, for example, a reference in here to get sizes, I think, and then that referenced a engine call, but that's no longer the case here. There is some duplicate calculations going on here. For example, you could write cosinus heading is this, and then sinus heading is this. What's happening here is a 2x2 matrix transformation where it represents the rotation matrix. So if we have a 2D rotation matrix, which is give or take right this here. If we compare that with the code here, we can see that we have a cosinus, minus sinus, sinus, minus cosinus. But this shouldn't be minus, I think, because it's not minus there. Oh well. But this is the, as far as I'm aware, two-dimensional rotation matrix. Did I just mess up fixing this? No. I'm pretty confident that this is wrong. This should be a plus. Alright, doesn't matter. We can look at that another time. Yeah, pretty confident it's wrong. Doesn't matter. But anyway, this function is now pretty decent in terms of performance. And that's pretty much it for this particular function right here. Now, I kind of forgot something doing at the start, and that is actually checking what we're dealing with in terms of performance. So, say we have an engineer. We've got 200 of them. And they're all assisting this. This enables the network statistics, and that shows us the simulation time. Typically, the simulation time is somewhere between 0 and 100. That means that we're running at +0, aka the game doesn't slow down. We have 100 milliseconds because they're 10 ticks a second. And if we reach more than 1 second, then the game starts to slow down, and that's where things become quite annoying. So this takes us about 10 milliseconds right now. But the issue is that the particle effects that we're seeing, that's actually what's taking up most of the time. Because this is actually only taking up, say, 3 milliseconds, 2.9, 3, 3.1, if the particle effects are not rendered. Which means that always when you do these type of evaluations for yourself to see what the actual change is, make sure that there are no particles rendered, because typically people play the game like this where you only see icons. People never play the game like that. So make sure that you do your tests in a more reliable manner. And we have about 2.8, 2.9 milliseconds. Now we can just switch back, working on create default beams. Check out every further deployment develop. But it's checking out, and then this file doesn't exist anymore. When you do a git check out, it doesn't know that you did this. So you gotta save this file once to trigger a reload, which it's not doing for some reason. Let me see what happens if I make an engineer. Nice. But does this not reload? Yeah. Alright, so now we have the old version of the function, which is just the one that we have here. Create default beams, create defaults. There we go, which is the old version that we had. Let's do the same thing. We have 200 engineers. Let's get rid of these. Wait for the effect to finish to make sure that doesn't really interfere with our test. Interesting enough, we have a error here, which I think is part of your pull request. All right.
Yeah.
Table index is nil. Oh wait, no, it's not part of your pull request. No, never mind. That's because I checked out to the develop branch to test the difference, but this file didn't update with that switch. But anyway, let's look at it. And right now we can see 3.5, 3.4, 3.2, 3.1, 2.9. Oops. 2.7, 2.8, 2.9, 3.2. It's roughly the same, but it has a few more spikes going up. Right now it's 3.2, 3.4. Always remember that the simulation speed is very much linked to your current CPU speed. So if this one toggles up a tiny bit, then that one toggles a tiny bit down. But let's say on average we have 3.1, 3.2, slightly lower than what we had before, right? Because in the previous version we never had it hit 3.4, 3.5. Now, by all means, that's a very tiny change, right? Doesn't seem too impactful if, for example, you compare it to a pull request that I was working on this afternoon about the impact of shields, where 5 Janus and 30 mobile shields can crush the entire sim. Right, so we have a reduction here of about 8 milliseconds per tick. So by all means, this is not a big fish in those terms. But it does show how we can approach a problem and how we can analyze the problem. And let me go back to the branch, optimize UEF effects. And more importantly, we reduce the stress on the garbage collector, because it's very easy to look at this number and think, oh, I made it faster. Right now it's at 3.4, 3.5. The previous version didn't get higher than 3.1, so we did do something good here. But the problem with a lot of the code changes that we've had in the past is that they didn't think of the garbage collector. So the garbage collector kicks in about every second, every 2 seconds. You can see that happen. Show stats, there we go. And then you go to the heap. And then in small blocks, at some point there you go, to roughly 19, and then it pumps back up to say 24. That's when the garbage collector kicks in and it picks up all the garbage that, all the tables, all the other information that no longer has a pointer to it, and it removes that. And what we did with this function when we were working on it, primarily we reduced the stress on the garbage collector. We didn't necessarily reduce the computation time that is needed to run all of this, right? Because in practice, the only thing we removed was this table that was being allocated here and being inserted here. But all the other functionality of this function is still essentially there. We just removed an unpack here, adjusted some access patterns to an up value or a global or a local, and removed some function calls. But what is really important in this case is the fact that we reduce the stress on the garbage collector. Because especially a year ago, if you would play a Cetan's game, maybe Tucket, I can remember that sometimes it would lag, it would stutter every 1 or 2 seconds. Maybe you know that happening. Yeah, that is the garbage collector saying hi. And that is something that this little number here is never going to tell us, because the garbage collector runs outside of the sim time, so it's not taken into account, the garbage collector here. But by making this function more friendly towards the garbage collector, we prevent those stutters creeping up slowly. So that is the primary change that we did with this function. In particular, in this while loop that we were doing here, with that vector that was hidden in there, every time this vector is made, we allocate about 64 bytes of a table, because the table itself and the pointers that it has to the hash part and the array part, and the fact that it has a few entries in it, allocates to roughly that amount. And we did that for every engineer, right? So every 0.3 to 0.5 seconds, we were allocating a table. And if you're thinking about the fact that people have factories here lined up, where each factory has 20 UEF engineers assisting that factory, or worse, then we are reducing the pressure on the garbage collector by thinking about that, in particular for this function, to prevent those stutters. So this is very roughly what I wanted to talk about with regards to this function. It's a bit disorganized. I wanted to, let's do it like that, by the way. I wanted to first do the performance check. You should always do the performance check first, see if what you're doing actually costs much. I did that this afternoon to make sure, and I forgot to do it at the start. But does what I did here make sense in terms of the workflow, the changes, anything else? Yes. Yeah, you could go further, and you could say, well, you know, what we're doing here is kind of nice and cute. We have a wait time that is in a range of 0.3 to 1.5, which means 3 to 15 ticks. So we can just, instead of doing this computation, we can do this. This is an overloaded function that can accept no arguments, and then it returns a number between 0 and 1, or 2 arguments, which is min-max. So we can do that, but then now it's always an integral number. And we can say, well, this wait seconds, if you look at siminit, is just this function that, given the number, waits a bit. So we can just say, well, we have here local yield is this, and then we can yield here wait time. So yes, we can totally still do this, and if we would, I don't think this would be noticeable in terms of the performance changes, right? Because the numbers that we're dealing with aren't particularly big. But yes, we can totally do this. And now I think it still looks the same. Yeah, still looks the same. Yeah. And there's probably more that we can do. For example, this get random offset. What you could do, and I think what you should do if you take this a step further, is that instead of doing the rotation that we're doing here every single time, we just compute the current square, the current rectangle that we're in, and then we just take a random point in that rectangle. Whereas right now we're doing a bit more than that with this cosinus and this sinus operation and stuff like that. So we could probably simplify this too if we would inline that manually in here, and then saying here we cache orientation and then here use orientation. And why can we do this? Well, the structure is always going to be oriented the same way. And if you look at, for example, a summit, say we have a summit, and that summit is damaged, say by this bomber. Now we're having here. Then if we would do this heal animation, it would compute the current orientation, but the moment we move and stop again, right, it doesn't work when it's, you can't repair units when they're moving. So you could be able to just cache the orientation in a rectangle and then skip those cosinus and sinus functions too. But I happen to know that these cosinus and sinus functions are lookup tables. They're not actually calling the sinus and cosinus instructions on the CPU. So it's not as bad as it may appear. Does this still work? My game is quite laggy. Yeah. All right. Does this make a bit of sense? All right. And by all means, this is a very small example of doing this. Let me get stage inline all the version. Another example, something that I did this afternoon, which was this one. I'll just quickly show what I've changed here, just to get an idea of what's going on. So what happened in here is that we have applied damage, and then from applied damage we go to this little fella here, create impact effect. So what happens in this pull request is that you've got all the other stuff that I did, right, with the using the cache idea here, but more importantly, what we're doing here is we're limiting the amounts of times that the impact effects actually spawn. So visually it still looks very much the same, right? If you would have a function of a shield, and then you would have 5 Janus, you have a Paragon 2, that's under the shield, you have 5 Janus. My game is terribly slow right now. Then now, what we simply did is, instead of every instance generating their own unique shield effect, we have only so many instances being generated, where visually it doesn't really matter. It still looks pretty much the same with the reduced amount of entities that we have here. Whereas the performance gain is pretty significant in this case. Right, we go from 10, 12 to 3.5. This one's a bit more tricky, I think, but it's the same idea of what we're doing, of what we were doing right here. Only in this case, there's not much we can do to reduce the amount of computations that we're doing, because in the end, we don't know how many instances are actually assisting the strategic missile defense. For example, if we would know that we already have 150 beams aimed at the strategic missile defense, then we could say, well, we may want to skip the emitters, right? Because it's not going to add anything to the visual appearance of the game, but we don't have that information in this function. So we can't go further than this in that sense. Let's take a quick break here before I continue and quickly look at what's happening in this particular function and what we can change it, because there are some significant things that we can change in this function.
One question.
Yes.
How does the function know like how many JNs it should visit?
Okay, so what I do here is it doesn't know how many JNs are hitting the shield, but it does know how many times it created the impact effect and if there are any impact effects alive at that moment. So every time this function is called, I just say, well, if we run, right? So there's some checks here. If we run, then we know that we have another live impact entity. And at the end of the function, we just reduce it by 1. Right? So that's and since this value, this self value, is part of the shield class, that means that each shield will track their own number of live impact entities. And with that, I can make an educated guess saying that, well, if we have a certain size, then we would expect a certain number of these impact entities to happen. So for the shield that we were having here, or here, does this reload now? Yeah. So if we go back to the shield, and then we give ourselves a paragon again. And we give ourselves some Janus. The shield cannot collapse if I'm not mistaken. Then every time those impact effects happen, I can keep track of that, and at some point they die again, so I know when to reduce the counter again. Right, so that's pretty much how I keep track of it here, but we can't do that here because well, we could technically keep it track in the unit being built by saying, well, unit being built dot alive engineers effects is 1 or something like that, and do the same thing that we do here, or that we do in this function. But we do not know when they're done, because they're either done because this while loop ends, which means that either the builder or the unit being built is destroyed. So that's not very likely, right? Because if we finish the building, then the builder and the unit being built are still alive, right? So we don't know by that, and there's no callback stating that an engineer has stopped assisting, right? So we're missing the capability of saying this in this function, and that's why we can't do the same thing here as we would like to do in terms of reducing the effect, so that if you are indeed assisting an SMT with 100 engineers or a factory with 100 engineers, the density of the effects is so many that it doesn't matter in practice, because the effect is there anyway, right? But we don't have everything we need, all the steps to keep some book, how do you call that in English, to keep track of those values accurately. And here we do, because this function is self-contained. At the end of it, the entity is destroyed again, so we have 1 less entity. Does that make sense?
Yes, and in the case of the shield, the function runs long enough that the other bolts are able to explode on the shield and hold the function again.
Yeah, so yeah, so every time this create impact is being called is again in a fork thread, which means that every one of these projectiles hitting the shields create their own thread and have their own execution, how do you call that? Execution path. Similar to the image that we had previously here. Right, so they're all done in the same tick, but they all have their own little execution path, their own variables, their own stack, etc. So they do not impact one another in that sense. They're all unique between quotation marks, but they're
If you run two functions after each other, then how like adding one at the beginning of the function and subtracting one affects the other function.
yes. Good.
Before you,
Say again.
there is a waiting between, so one add one waits, does its thing, and then subtracts when it's done, and then accessing the same variable in between.
All right.
Oh, it is.
I didn't notice that we went from 4 people to like 10, so that's interesting. Okay, so exactly. So what happens is that this is being executed, and then the wait function is there, which means that this moment here is reached, and then the next one can go. And then the next one does exactly the same thing, but then with its own parameters. And the thing that is shared in this case is the shield itself, right? So this self here is the same between the different threads. That's why we can add this value here and know that for the next projectile that's going to happen, it's going to let's say this started at 0 and we have a projectile. So then we would put this on 1, then the next projectile is guaranteed to start at 1. Assuming that this wasn't run yet, of course. Right? But this is the shared bit of information between the threads, which is the self in this case. Alright, let's take a 5-minute break, and then I'm going to look at this function right here. I'm not going to actually do all the code, but I'm just going to show you the amount of garbage that this function does and how ridiculous it is by doing essentially the same thing that we just did, by just looking at the function and saying, okay, so is this used, yes or no? Do we need a table allocation, yes or no? And by replacing this entire bit with some mathematics, which would allow us to prevent all of these table allocations and this table.remove operations and etc. And replace it with some interesting mathematics. But I'm gonna get something to drink, so I'll be right back. Yes, commercials.